This lecture is going to be over chapter 1 out of Khan. You can see here, this is a PDF copy I have of Khan, where we're going to discuss the structure of matter here, chapter 1. A lot of what you're going to see here in all of these sections is going to be discussed in this slideshow presentation. It's kind of a summary of what's going on here in these 10 sections. So, but reading the text would be good. Particularly, I'd focus on just doing the summary, looking over the slides, and then trying to go through and look at some of the problems here. I will also be working some of the problems in separate videos as we go along. So let's go back to it here. So we're looking at the structure of matter. All right. So we have our atom here. We have what looks like a planetary model. We have the nucleus here. And then you have ground state electrons here. Those are the closest to the nucleus. You've got other states that surround that and can orbit. And this is a simplified model of what we see in the atom. It's not something that we actually see, but for our purposes, this is how we're going to look at it. So we have electrons here in a ground state, and we have electrons here that are in higher levels around the atom. These can fall to lower levels depending on the circumstances. So that's something we're going to look into here. Each atom consists of a small central core and then surrounding clouds of electrons moving in orbits around the nucleus. There is actually an app out, I know in the Apple store, where you can see what the clouds of atoms around the nucleus actually look like. It's something I had in graduate school. That's quite interesting. Originally, it was thought to be the smallest and indivisible particle of matter. The atom is now known to have a substructure that can be divided into smaller components. The radius of an atom, or the radius of the electron orbits, is approximately 10 to the minus 10 meters. Very, very small. So, basic properties of nuclei. Nucleus is going to be a dense, positively charged body. It's going to consist of neutrons, which have no charge, and protons, which have a positive charge. If you group neutrons and protons together, they're going to be classified under one name called nucleons. Mass of a neutron and the mass of a proton are roughly the same. And the mass of a nucleon is approximately 2,000 times that of an electron. So, properties of atoms are derived from the makeup of their nuclei and the number and the organization of the orbital electrons. So we've got two fundamental particles, protons, neutrons. Protons are going to carry the positive charge. Neutrons will not carry any charge. Electrons, of course, have the negative charge. The number of protons in the nucleus is equal to the number of electrons outside the nucleus. Now, what happens whenever an electron gets added or stripped away, then you end up with ions. But if you're looking at a neutral atom, then the number of electrons and protons are going to remain the same. So atomic nuclei are represented by the notation X, where A is the atomic mass number, Z is the atomic number, and X is going to be the chemical symbol. The number of protons is equal to Z, and the number of nucleons is equal to A. You can find the number of neutrons by taking the difference. You're always going to have more of these than you will this or this. So when you subtract out the number of protons from the number of nucleons, you'll get the number of neutrons. So here's a small scale of an atom where you got electrons circling around it. And if you look at those protons and neutrons, you'll find that they're made up of quarks and gluons. So the example here is that you have a chemical symbol, X. You have the number of nucleons up here. You have the number of protons here. Sometimes you'll see it written out where you'll have the number of neutrons written over here, AZN. So for instance, if we look at hydrogen, hydrogen has one nucleon that happens to be a proton, so you don't have any neutrons. If you were looking at just regular helium, you would have 4 nucleons, 2 of which are protons. As you've probably guessed by now, 2 of those other nucleons are neutrons. So what are the basic properties of nuclei? The chemical identity of an element determined by the number of protons in the nucleus. So the number of protons are going to tell you exactly what the chemical identity is. So gold is going to have a different number of protons in it than would silver, than would tin, than would copper. So that arrangement of protons in the atoms are going to tell you what sort of element you are dealing with. Under normal circumstances, an atom is going to be electrically neutral. Number of electrons will equal the number of protons. So the number of electrons in an atom is going to determine its chemical behavior. And right now we know, I think it's more than 100, but around 100 different known elements, some of which have trouble remaining in existence for very long. So basic properties of nuclei. All right, so 2 atoms that have the same number of protons in the nucleus and a different number of neutrons will be chemically identical. So in other words, carbon 12, carbon 13, carbon 14, they all have the same number of protons, but the number of neutrons are going to differ from each of those atoms I specified. 2 atomic nuclei with the same number of protons but a different number of neutrons are called isotopes. Iso meaning the same, topes, if you can remember this, the P in topes is the same as protons, so same number of protons. So for hydrogen, we have light hydrogen, we have heavy water, deuterium, nucleus is called a deuteron, and we have tritium, or heavy hydrogen, and that is considered to be radioactive. So nuclides, isotope, atoms having nuclei with the same number of protons but different number of neutrons. Again, isotope. Look at the P, iso meaning the same. Isotone, same number of neutrons but different number of protons. And yes, that can happen. Isobars, same number of nucleons but different number of protons. And isomers, same number of protons as well as neutrons. These represent identical atoms except that they're in they differ in their nuclear energy states. So you've got xenon here. You've got something as 131M. I think the M there stands for metastable, and as well as just having the regular element. So Again, isotope is going to be the same number of protons. Isobar is going to be the same number of nucleons. Isotone is going to be the same number of neutrons, and isomer is going to be a metastable state. So if you can remember what vowel or consonant here is underlined here towards the end of the name, then you can see exactly, or try to remember, what name to use for each of these situations. So, nuclear stability. Certain combinations of neutrons and protons result in stable or non-radioactive nuclides than others. Stable elements in the low atomic number range have an almost equal number of neutrons and protons. So Z is roughly equal to N. But as Z increases beyond 20, the neutron to proton ratio for stable nuclei becomes greater than 1 and increases with Z. And the reason is you need more and more space in order to be able to add more and more protons in there. And the only way you're going to be able to get that is adding in more and more neutrons. And so here, if you take a look at this, you got your proton number here, you've got your neutron number here. If you were to draw a dashed line here that showed you equal numbers of neutrons as well as protons, you can see the dashed line writing here. As your proton number increases, you can see that the stable nuclei follow this trajectory. And what you are finding out here is that the value of N is going to be greater than the value of P as these lines separate. So nuclear stability is going to be analyzed in terms of even and odd numbers of neutrons and protons. "300 different stable isotopes, more than half have even numbers of protons and neutrons and are known as even nuclei. About 20% of the stable nuclei have even Z and odd N, and about the same proportion have odd Z and even N. So you're looking, 20% for this case, about 20% for this case, the rest falling here. So masses of atoms and atom particles are given in terms of atomic mass units. We ascribe this because, as you can see here, one atomic mass unit is a very, very small amount when measured with kilograms. So sometimes it's just easier to work with these small units. So an atomic mass unit, or AMU, is going to be 1/12 of the mass of a carbon-12 nucleus. The atom is arbitrarily assigned the mass equal to 12 AMU. We could have picked any other standard, but carbon's pretty ubiquitous. So because of that, since you can pretty much find it at the drop of a hat, we can work with it by assigning it a definition, or assigning a definition to that property. So the mass of an atom expressed in terms of AMU is known as the atomic mass, or the atomic weight. Again, mass is something different from weight, but in this particular circumstance, it's the nomenclature will be roughly the same. Gram atomic weight is defined as the mass in grams numerically equal to the atomic weight. So Avogadro's law. Every gram atomic weight of a substance contains the same number of atoms. So the number, referred to as Avogadro's number, or Avogadro's constant, N sub A, the currently accepted value is 6.0221 times 10 to the 23rd atoms per gram atomic weight. Gram atomic weight, we're looking at using the same definition as mole. So Avogadro's law. We can calculate other quantities of interest, such as the number of atoms per gram, grams per atom, and electrons per gram. So the number of atoms per gram, Avogadro's number, divided by the atomic weight. Grams per atom, atomic weight, divided by Avogadro's number. Just take this and flip it around. Number of electrons per gram is Avogadro's number times Z divided by the atomic weight. And we'll go over some problems on that. So atomic mass and energy units. Masses of atomic particles, or AMU. You can see there that the protons and the neutrons are very, very close to each other, but not equal. So the neutron weighs a little bit more than the proton does. And the electron is going to be about 1/2000th of a neutron or proton. All the atomic masses in units of AMU are very nearly equal to the mass number. But the mass of an atom is not exactly equal to the sum of the masses of its constituent particles. You would think that if you had an atom that had 6 protons and 6 neutrons in it, that if you add together all of the constituent particles, that you'd come up with a mass of the atom. It's what you do for everything else in existence, right? It's a little different. We'll find out a little bit more about that. So when the nucleus is formed, a certain mass is destroyed and converted to energy to keep the nucleus together. So that mass turns to energy, which acts as a glue to keep the nucleons together. The mass difference is called the mass defect. An amount of energy equal to the mass defect must be supplied to separate the nucleus into individual nucleons. So in order to split them apart, you're going to have to add energy to that in order to be able to produce this. So the basic unit of energy is going to be the joule. It's equal to the work done when a force of 1 Newton acts through a distance of 1 meter. The Newton is a unit of force. So the product of 1 kilogram mass and the acceleration of 1 meter per second squared. It's the more convenient energy unit in atomic and nuclear physics is the electron volt. When we're looking for things at a very small level, this unit comes into play. These types of units are usually good when we're looking at everyday objects. And not to say that these aren't everyday objects, these are just small, very small everyday objects. So, electron volt. It's kinetic energy acquired by an electron in passing through a potential difference of 1 volt. The work done in this case is given by the product of the potential difference and the charge on the electron. So 1 eV is 1 volt times the charge on the electron. And you'll notice that you come up with joules. Is the joule the same as what we are discussing up here, basically 1 Newton meter? Yes. Energy units, energy being measured in joules, it's the same concept on the macroscopic level as it is on the microscopic level. It's just we have smaller units here to be able to work with at this particular level. So 1 kilo electron volt is going to be 1000 eV, and 1 mega electron volt, and you'll start to see this term more and more, is going to be 10 to the 6th electron volts. So, what is Einstein's principle of equivalence of mass and energy? His famous equation, E is equal to mc squared, probably the most famous that he's written down, is showing how mass is equivalent to energy. What is C? C represents the velocity of light. So the energy of 1 kilogram, multiplying it by the speed of light squared, is 9 times 10 to the 16th joules, or 5.62 times 10 to the 29th mega electron volts. So the mass of an electron at rest is sometimes expressed in terms of its energy equivalent, or E naught. Electron's mass is going to be 9.1 times 10 to the minus 31 kilograms. Using the energy mass conversion there, you find out that the energy equivalent, or the rest mass, is going to be 0.511 mega electron volts. If you convert AMUs to energy, what you find is that 1 AMU is equal to 931 MeV. E is equal to mc squared. The equivalent mass of any particle of total energy E is going to be given by taking E and dividing it by c squared. In other words, if you take this equation, divide both sides by c squared, you just end up with mass on this side. So how would you express mass of particles in units of GeV, giga electron volts, divided by c squared? Well, 1 giga electron volt divided by c squared is 1.0723 AMU. So what if we consider the effect of a particle on its mass? So high-speed particles have shown that the mass of a particle depends on its velocity, and it increases with the velocity. So the relationship between mass and velocity can be derived and using Einstein's theory of relativity. So if m is the mass of a particle with velocity v and a rest mass of m sub naught, then the mass is going to be equal to all of this. We know the kinetic energy is going to be the mass times c squared minus the rest mass times c squared. Factoring all of this out, doing some math, this is what we come up with. So the relativistic effect of velocity on the mass becomes important when a particle travels with a velocity comparable to that of light. And generally, you have to be going roughly somewhere about 10% of the speed of light or more to start factoring that in. So this is a pretty good quote here. An expert is a man who has made all the mistakes which can be made in a very narrow field. So electrons revolve around the nucleus in specific orbits. They are prevented from leaving the atom by the centripetal force of attraction between positive charges in the nucleus and negative charges, of course, in the electron. Using classical physics, an accelerating or revolving electron must radiate energy. The result is a continuous decrease of the radius of the orbit, with the electron eventually spiraling into the nucleus. The problem is that doesn't happen. So what's going on? So we found the emission or absorption of radiation by elements reveals that the change in energy is not continuous, but it is discrete. So we've got two fundamental postulates. Electrons can exist only in those orbits for which the angular momentum of the electron is an integral multiple of h divided by 2 pi, h being Planck's constant, which is given there 6.626 times 10 to the minus 34th joules seconds. No energy is gained or lost while the electron remains in any one of those permissible orbits. Seems strange, but that's the way it is. So an arrangement of electrons outside the nucleus is governed by the rules of quantum mechanics and the Pauli exclusion principle. So simplified, the innermost orbit or shell is called the K shell. This one right here. So you got your nucleus right there. You got the K shell. The next shells are L. And then if you were to add them on, you'd have M, N, O, so on and so forth. The maximum number of electrons in a given orbit is given by 2n squared. So a shell doesn't need to be completely filled before the electrons begin to fill the next shell. So the number of electrons in the outermost shell reaches 8 additional electrons, and it begins to fill the next level to create a new outermost shell before the electrons are added into the lower shell. Electrons in the outermost orbit are called the valence electrons. Those are the ones that are grabbed or paired with other electrons more easily than any of the others. The chemical properties of an atom depend on the number of electrons in the outermost orbit. Electron orbits can also be considered as energy levels. Potential energy of the electrons and opposite sign, it may also be called the binding energy of the electron. So here's an example. You have a K series here, very close, that's the lowest level. And you have L, and you have M, and N, so on and so forth. So this is a tungsten atom. So you've got a few possible transitions shown here, not all of them, but a few. And then 0 of the energy scale is arbitrarily set at the position of the valence electrons where the atom is in the unexcited state. So you've got electrons in the outer orbit here. They're not being excited by anything. That's going to be considered to be 0 for the energy scale. Binding energies for the higher Z atoms are greater because of the greater nuclear charge. So what you're going to see here, you're going to see atoms that could fall from electrons that could fall from here to here, or perhaps in the next lower shell to here, or maybe the next lower 2 shells or 3 shells or something along those lines. You can also see these valence electrons fall maybe into not the lowest shell, but the next lowest shell. And when that happens, you're going to have an energy difference here that you're going to have to describe. So if we took a look, and that should be a deuterium nucleus, you've got 1 proton and 1 neutron. So if you take the mass, the rest mass of a proton and the rest mass of the neutron, this is what you come up with. If you actually were able to find a way to measure the mass of the deuteron, what you would see is this would be the number of AMUs you would come up with. This is going to be different from this. And that suggests that some energy is going to be necessary to separate a deuteron into its independent free particles. And that difference is going to be referred to as the binding energy. So when you go through and you take the difference, you find out that the binding energy is going to be this. If you take the number of AMUs and convert that to MeV, this is what it comes up to. So the minus sign here signifies energy has to be absorbed by a deuteron to separate it into a free neutron and a free proton. It won't do that naturally. It's got to have energy in order to be able to do that. And that's why that is considered to be negative. Energies associated with nuclei on the order of megaelectron volts. Chemical reactions involve transfer or sharing of electrons between atoms. Valence electrons normally occupy outer shells. Energy imparted to a valence electron to raise it to a higher energy orbit creates a state of atomic instability. So-called valence electrons are responsible for chemical reactions, bond between atoms, and the emission of optical radiation spectra, normally that occupy the outer shells. The electron will fall back into its normal position with the emission of energy in the form of optical radiation. The energy of the emitted radiation will be equal to the energy difference of the orbits between which the transition took place. So if the transition involved inner orbits such as K, L, and M, any of those shells where the electrons are more tightly bound, the absorption or emission of energy will involve higher energy radiation. If sufficient energy is imparted to an inner orbit electron so that it is completely ejected from the atom, the vacancy or hole created in that shell will be almost instantaneously filled by an electron from a higher level orbit. So to conserve energy, this transition would be accompanied either by an emission of radiation, such as a characteristic X-ray, or the ejection of an outer shell electron, known as the Auger electron, I believe. Yeah, I don't believe you say that as Auger. I believe it's Auger or Auger. I forget. Auger electron. That's it. Auger, I believe, is a sauce, actually. When a bombarding electron collides with an electron in an inner shell of the atom with sufficient energy to remove it, then you've got a vacancy. So you've got some high-speed electron coming in here to the atom, and you have, boom, some sort of energy here that is imparted. You can even just eject that particular electron, leaving a vacancy here. And the vacancy is filled when an electron in a higher orbit drops into the vacancy to fill it. So remember that it's accompanied by an emission of radiation, that characteristic X-ray. So for nuclear forces, you have several here. You've got a strong nuclear force that holds the nucleons together. You've got electromagnet, which is strong between charged nucleons, but it's repulsive, and it tends to disrupt the nucleus. In other words, just keep stacking positive charges in there, they're going to want to push away from each other. You have the weak nuclear, which appears in certain types of radioactive decay, and then you have gravitational, which is not going to really enter into what we're doing here. So for nuclear forces, they are short range. A distance is smaller than the nuclear diameter. A potential well, which is what you're seeing here, is formed as a result of the mass defect and provides the nuclear binding energy. And it acts as a potential barrier against the nucleon escaping the nucleus. In other words, once you're in here, it's very hard to get out outside of tunneling, which we're not going to talk about here right now. So the energy level diagram, you have a particle in a nucleus. If this is a particle with no charge, you might see something like this, where there is no decay like what you see here. If you've got a particle with a positive charge, so this would be a neutron, this would be a proton. So the potential function here is going to be the potential energy as a function of the distance from the center of the nucleus, which is represented right here. This B here is going to be the barrier height, and the R here is going to represent the nuclear radius. If a positively charged particle approaches the nucleus, there's going to be a potential barrier due to the Coulomb forces of repulsion. In other words, exactly how many more positive charges are you going to be able to add because there ain't no room. But this is going to prevent the particle from approaching the nucleus. But let's say the particle is able to get close enough to the nucleus to be within range of the strong nuclear force. In other words, the electrostatic is going to try to push it away, but the strong nuclear force may say, well, all right, fine. We'll all stick together. So the repulsive forces here are going to be overcome, and the particle is going to be able to enter the nucleus. This process is going to be described by wave mechanics. And these are particles that are considered associated with de Broglie waves. So let's say you've got cobalt-60 here, and that nucleus is made radioactive in a reactor by bombarding cobalt-59 atoms with neutrons. As you can see here that the proton number is the same. And let's see if you can remember what these two atoms are. There's a special name if you remember from earlier on. And if you said isotopes, you're doing well. So the excited cobalt-60 nucleus first emits a particle. It's a beta minus particle. Then in two successive jumps, packets of energy are released. So you've got the beta minus particle being released. It's possible that it could be released here with the energy maximum being 0.032, or it could be about 0.1% of the time a beta particle released with this amount of energy. And then you see two gamma decays after that. And it eventually ends up as nickel. So the emission of the beta minus particle result of the nuclear transformation. So one of the neutrons in the nucleus disintegrates into a proton, an electron, and a neutrino. It's kind of weird, isn't it? The electron and the neutrino are emitted instantaneously and share the released energy with the recoiling nucleus. So all three of those are going to end up sharing in the radiation that's released. So if we look at particle radiation here, we're looking at the scales of these things. You got 10 to the minus 18th, which describes quarks. You've got an electron here, which is a little bit above that. Got protons at 10 to the minus 15th. Then you got a nucleus at 10 to the minus 14th. And then you've got the scale of the atom, which is 10 to the minus 10th. So radiation applies to the emission and propagation of energy through space or a material medium. Particle radiation, energy propagated by traveling corpuscles that have a defined rest mass and a definite momentum and definite position at any instant. So distinctions between particle radiation and electromagnetic waves. These represent modes of energy travel, and there's a hypothesis introduced concerning the dual nature of matter. Is it a particle? Is it a wave? Yes. Theorized that not only do photons or electromagnetic waves sometimes appear to behave like particles, they exhibit momentum, but also material particles such as electrons, protons, and atoms sometimes have types of wave motion associated with them, like refraction. So where do you draw the line? Are they particles? Are they waves? Yes. Many other atomic and subatomic particles have been discovered. Travel with high speeds, depends on their kinetic energy. They never attain exactly the speed of light in a vacuum. And they interact with matter and produce varying degrees of energy transfer to the medium. So you can see more of a description regarding fermions, bosons, all of the kinds of description of subatomic matter. So, a mode of energy propagation. So you've got light, you've got heat, you've got radio waves, you've got microwaves, ultraviolet light, X-rays, gamma rays, all sorts of different ways. So Maxwell, James Clerk, first described these radiations in terms of oscillating electric and magnetic fields. What you will find is that when you look at electric or magnetic fields, there's a pairing between the two, and that's important. So here is an example of that. You've got an electromagnetic wave at a given instant of time. E and H are respectively the peak amplitudes of the electric and the magnetic fields. The two fields are perpendicular to each other. So energy is propagated with the speed of light in the z direction. So c is going to be the velocity of propagation. V here is going to be the frequency in cycles or hertz. You've got lambda here, which is the wavelength in meters. So you can see the description here, wavelength in meters. The very, very long waves here are radio waves. You start getting shorter and shorter. You can see the TV radar. And then eventually, if you continue to dial up the energy, what happens to the wavelengths is that they get shorter and shorter and shorter. So by the time you get to X-rays and cosmic rays, they're very, very short. So a very small portion of the electromagnetic spectrum constitutes visible light bands. Wave nature of the electromagnetic radiation can be demonstrated by experiments involving interference and diffraction of light. In other words, if you look at the slit experiments or dual slit experiments, you can see interference patterns and diffraction, things of that sort. Similar effects have been observed, like X-rays using crystals, which possess interatomic spacing comparable to X-ray wavelengths. Wavelength becomes very small or the frequency becomes very large. So dominant behavior of electromagnetic radiations can only be explained by considering their particles or their quantum nature. So to explain the results of certain experiments involving interaction of radiation with matter, you've got to take into consideration the photoelectric effect as well as Compton scattering. And those are two things we'll go over a little bit later. We've got to consider electromagnetic radiations as particles rather than waves. E is equal to HV is used to find the amount of energy carried by these waves. E is, of course, going to be the energy. H is going to be Planck's constant. And V, or nu, actually, if it's a Greek letter, is going to be the frequency. If you combine this equation, speed of light is equal to the frequency times the wavelength, and E is equal to HV, and you come up with this. This was actually, I think, one of the homework questions. If E is to be expressed in electron volts and lambda in meters, since we know what 1 electron volt is equal to here, we know that the energy is going to be equal to this. So as the wavelength becomes shorter, since it's in the denominator, or the frequency becomes larger, the energy of the photon becomes greater. That is a short summary of what we're encountering in here. In week 1, I will record some additional lectures to kind of go over some of the points.